Hi, everyone. So it's so great to be here. Beautiful weather, and beautiful science, so can't really get much better than that. And hopefully everybody can hear me okay? Yeah, okay. So I'm going to talk about both the Arctic and the Antarctic. And the title of my talk is really broad and vague. And I want to clarify, I'm not talking about all changes in the climate. I'm really not going to talk about ice sheets at all. And so this is really going to have somewhat of a sea ice focus and a polar amplification focus. You'll see there's going to be some overlap with some of the talks that we saw earlier in the morning. And I also have a climate modeling bias. So I work at NCAR, we're a climate modeling center. I think about climate models all day long, every day, especially because we're putting together our next version of the CESM model right now. Okay, so I think, and this again overlaps with some of what we saw earlier today, when thinking about changes in polar regions, for me, it's very useful to think back to the feedbacks that are at play. And so, of course, we have both radiative feedbacks and non-radiative feedbacks. And this schematic from this review paper by Goose et al. Back in 2018 kind of nicely illustrates that there's many different things at play in the polar regions. And I want to highlight that there's some factors in polar regions that are unique and lead to unique influences on these feedbacks. So, of course, there's cold temperatures. That means that the Planck feedback is weaker, so it's a negative feedback, but it's a weaker negative feedback in these cold temperatures than it is in the rest of the globe. So that would lead to amplified warming in cold regions. There's also, of course, the presence of ice and snow. That leads to surface albedo feedback. It also influences the lapse rate feedback that we heard about earlier. Stable atmospheres, we can argue about whether this is important for the lapse rate feedback, yes. But it does help to amplify warming at the surface, and that leads to a positive lapse rate feedback in the Arctic that contributes to amplified warming there. And then finally, we have cold ocean temperatures. That means that density in the ocean is strongly controlled by salinity. So things like ice growth, brine rejection, ice melt, or ice and freshwater discharge from land ice can all influence ocean circulation, ocean mixing, and affect feedbacks in these regions. Of course, ice sheets and ice shelves have their own feedbacks associated with them, in addition to affecting interactions with the ocean. I'm not going to talk about those feedbacks, but I think there's a lot of people that are experts on that in this room, and I'm sure we'll hear more about it during the week. It's a region of polar night, so we have months with no sunlight. That affects things like how effective shortwave cloud feedbacks are. And finally, what I'll get to throughout the talk is the fact that these different aspects of cold polar climates differ quite dramatically in the Arctic and the Antarctic. And that leads to different warming responses in those two different regions. And so it's also important to note that feedbacks are interactive. These things are not isolated. For example, there's been a lot of nice work done showing that the lapse rate feedback, surface albedo feedback are interactive and related to each other, and they're both strongly influenced by sea ice and sea ice loss. So these feedbacks will influence how much change we get in polar regions, of course. And of course, we've observed changes in the polar regions. I'm not going to go through this in a lot of detail because other people have covered it previously. But of course, we've seen warming across the globe. So this just shows temperature changes over time as a function of latitude. And we've seen this amplified Arctic warming signal emerge. We also have seen dramatic changes in sea ice cover. So in the Arctic, it was very clear in the early 2000s that sea ice was being lost dramatically. We have had low sea ice cover throughout the 21st century so far. And that's in contrast to what's been observed in the Antarctic, where there were increases in sea ice occurring until 2014, 2015 or so, and then this very rapid sea ice loss that occurred in 2016 and has continued since that time. So there's definitely different characters of changes happening in the polar regions in the historical record. So I'm going to start by talking a bit about what's happening in the Arctic. And again, this has some overlap with some of the previous talks from this morning. And so models have consistently projected that we should see amplified warming in the Arctic. And so this is actually a figure from this Manabi and Stouffer paper back in 1980, showing warming as a function of month and latitude, highlighting this amplified warming in the Arctic, the fact that it has this seasonal characteristic of enhanced warming in the fall and winter months, and actually very little amplification in the summer. That is something that, of course, has now been observed. So those model simulations predicted that well before it emerged in the observational record. So this shows from the GISS temp observations that latitudinal and seasonal structure. It looks very much like that plot from Manabi and Stouffer back in 1980. And if you look at the amplified warming and how it's changed over time, that's what's shown here. It's in terms of an amplification factor. So a value of 1 would be when the warming in that 70 to 90 north region is the same magnitude as the globe. And you can see from this that amplification, if you're looking at a 10-year running mean air temperature change in the Arctic, didn't really emerge until the late 20th, early 21st century or so. The exact date will differ depending on how you define amplification. But it also shows that the amplification has perhaps increased over time. And so there's some suggestion that the strength of amplification can change. And that could be due to internal variability, could be due to the strength of those feedbacks. And so we wanted to look into this a little bit more. And in order to do this, we used this multi-model large ensemble. And so this, when we did this study, there were 7 models available that had all done single model large ensemble simulations. And so these model simulations allow us to really robustly characterize the forced response in the system versus internal variability. So each individual model has run multiple ensemble members. By averaging across those ensemble members, we have a measure of the forced response, because those simulations are all subject to the same external forcing and an identical model. And then we can also look at the internal variability in those simulations by looking at the spread across ensemble members. So this is something that is now fairly routinely done in climate modeling simulations, but it wasn't actually, some of the early studies used just single members of simulations to diagnose change. The nice thing about this multi-model large ensemble is that we also can look across models to see where responses are robust, why models differ, and that can give us information on the processes that are at play. Okay, so when we look across all of these simulations, we find that this enhanced warming, its seasonal structure, are all very consistent across models. And this is true for these models, it's true for basically models in the CMIP archive, et cetera. And that seasonal structure can be understood, at least in part, because of changes in the surface heat fluxes. And others have mentioned this, I think Patrick mentioned this in his talk, but just to show what that looks like. So in the summer months, you get absorption of heat due to solar radiation at the surface that causes the ocean to warm, causes sea ice to melt, and then that heat is released back to the atmosphere in the fall and winter months, leading to that amplified warming in air temperature at that time. So how is this Arctic amplification influenced by internal variability? So what I'm showing now is the amplification factor. So this is an annual mean for running decadal means over the 1980 to 2100 time period. And so the range across the simulation is shown in the gray. So that's the internal variability. And the dark black line is the forced response. And so you can see that an anthropogenic signal in Arctic amplification emerges around the year 2000. So basically you see in all ensemble members around that year, they all have an amplified response in the Arctic relative to the global mean. But you can also see that the actual magnitude of it is highly variable. So internal variability has a really strong imprint on how amplified the warming is in the Arctic across these different models. So how does the forced response in Arctic amplification change over time? So the forced response is this black line here. You can see that by the end of the 21st century, the scatter, so that amplification factor across the different models, is strongly related to its sea ice area change. And you can also see that it differs in terms of its characteristics in how it changes across the different models. So several models have a decline in their amplification magnitude. Others have a very modest change in Arctic amplification, a modest decline, and some others basically have no change at all, but have some interesting, perhaps multi-decadal variability. So they all differ, and it's hard to say which of these models is right. So it's useful to look at the processes that could be driving these changes in amplification and how they differ across the models to get some insight onto what might actually be realistic. And so in order to do this, we analyzed the surface albedo feedback and how that feedback is changing, and we used a radiative kernel method to do this. And unfortunately, we didn't have the necessary output to do this for all the models, so here I'm only showing 5 models. But what we found is that several of the models had sizable declines in their surface albedo feedback over the 21st century, and other models had little or no change. And that corresponds very strongly with their Arctic amplification signature. So it looks like there's a suggestion here that the Arctic amplification signature is in part associated with how the albedo feedback evolves in these models. So we can dig into this more and look at the spatial patterns of the surface albedo feedback and how it's changed over the 21st century. And so if you just look at this, broadly, you see that the models differ dramatically. They have increases in feedback, decreases in feedback across different regions of the Arctic. But if you look a little bit more carefully, you see that there's some consistency. So these models have reductions in the surface albedo feedback in areas that have become ice-free in the summer. So basically, the albedo feedback saturates in those regions. You can see that the regions differ, and that's because of different biases across the different models. But albedo feedback saturates in regions that have become ice-free. And so that albedo feedback is reduced. We also see some evidence of something similar happening in some terrestrial snow-covered regions. And we assume that that's, we didn't look into this in terms of looking at the snow simulations in these, but we assume it's related to the snow-free season in those models by the end of the 21st century. And then you see that there's an increase in surface albedo feedback in these regions of thicker ice cover, where by the end of the 21st century, they're starting to see significant sea ice losses in summer months in those regions, and in particular in kind of earlier summer months. Many of these models have gone ice-free by 2050 or so, but you're starting to see that there's significant ice loss in those regions earlier in the summer when the sun is at its peak and really impactful. So the average feedback changes in these models result from these many different factors that are time evolving, that have implications or influences from the biases across these different model states. And so by looking at this, it can give us some information about what's actually realistic. What kind of patterns of sea ice thickness and things like that might be leading to one model having a lot of sea ice loss in the East Siberian Sea and another model having very little sea ice loss in the East Siberian Sea. things like that. So just to note, the seasonality of warming also changes over the 21st century. So this shows that seasonality in terms of surface air temperature trends. And the y-axis here is a little different. It's moving from September on the bottom through August on the top. And so basically what you're seeing is that the maximum trends in surface air temperature change get later into the year, starting out in September, October, November, but then moving into kind of January, February, March. That's associated with changes in when the turbulent heat fluxes are being released back to the atmosphere. And that, of course, is related to trends in the sea ice area and how those are expressed seasonally. And the fact that, you reach ice-free conditions in September. This is just shown as an example for the CESM1 CAM5 model. But then those ice trends get larger and larger later into the fall and winter months. So how do things evolve with continued and very extreme sea ice loss? So I'm going to go through this quickly because I want to get to the Antarctic stuff. But this shows in these RCP 8.5 extension simulations that go out to 2300 and have very high rates of anthropogenic forcing, so really extreme scenarios. In the CESM1 model that we used for this analysis, the model reaches ice-free conditions, completely ice-free conditions by 2200. So these are really extreme. What I'm showing here is the simulation of trends. So these are decadal trends in sea ice cover as a function of month and year throughout these integrations. When the contours go black, that's because ice is lost in that month. And so you see initially, there's large ice losses in the fall, moving into the winter months, and then you start to see spring and early summer ice loss becoming a maximum. And this influences the amplification of warming in the Arctic, so this is a time series of that, and the surface albedo feedback. And so at the end of the 21st century, we've lost sea ice completely. Around mid-21st century, the albedo feedback declines, and that's this period of really modest sea ice loss, and you see the albedo feedback declines as well. Then there's this increase in the Arctic amplification and increase in surface albedo feedback that's associated with this really rapid sea ice loss that's occurring early in the summer when the sun is very high and has a really big influence on the shortwave budgets. And then finally, the albedo feedback weakens, Arctic amplification declines as you saturate that feedback by reaching ice-free conditions all year long. So those are the kind of characteristics that are important for driving some of the surface changes in the Arctic. What about the Antarctic? So the Antarctic is a really different place. Sea ice processes differ. There's a strong role for the ocean on surface climate. There's the presence of ice shelves and ice sheets and interactions of those with the climate state. There's strong teleconnections from the tropics. And there's also a historical influence of stratospheric ozone loss. And I'd say a lot of the research on Antarctic change, or at least the research that I've been involved in, has really been thinking about these topics. What are those teleconnections from the tropics? What's the role of the ocean? What is the influence of stratospheric ozone loss? And those questions are really important and give us insights into how the Antarctic is working. But in terms of thinking about amplification of warming, what we find is that the Antarctic has very little amplified warming. And again, Manabe, there's a reason he won a Nobel Prize, back in 1992, showed this. So this shows in transient climate-coupled ocean-atmosphere model simulations, the latitude and month structure of warming in response to rising greenhouse gases. So you see your kind of classic Arctic amplification signal, but you see very little amplification in the Antarctic. And this is consistent with models, these more recent models. So this shows that amplification factor is a function of latitude, showing that, again, in the high southern latitudes, you have very little amplification, and actually many of these models have less warming there than the rest of the globe. So Manabe explained this back in 1992 as this increase of surface air temperature is weak because of the vertical mixing of heat over a deep water column. So the role of the ocean in driving that response. So we have learned a lot since 1992. And there's been a lot of nice work, actually documenting feedbacks in the Antarctic. Again, this is from this review paper back in 2018. And what's shown here are the kind of this classic feedback analysis, Antarctic warming on the y-axis, Arctic warming on the x, and then things on the one-to-one line, giving you an indication of whether there's amplification in the Arctic below the line or Antarctic above the line. And so what this study found, and this is consistent with other studies, is that the Planck response, albedo feedback, water vapor feedback, all drive warming in the Antarctic, but they drive a weaker warming than you get in the Arctic. So those feedbacks are typically weaker. The lapse rate feedback has little impact. Cloud feedbacks are actually negative and lead to cooling in the Antarctic. And ocean heat uptake, this term that was called out by Manabe back in 1992, leads to less warming in the Antarctic and a lack of Antarctic amplification, or at least it's a contributor to that lack of Antarctic amplification. So there's a lot of indications that the ocean in the Antarctic is really important. It's really important for the anthropogenically driven response. And it also looks like it's very important for changes occurring recently in the sea ice system in the Antarctic. And so there's a lot of different evidence and a lot of suggestive evidence that the ocean in the Antarctic, the Southern Ocean, is contributing to some of the recent sea ice changes that have occurred. So this is just one of those studies. So this is some work led by Jerry Meal back several years ago now, where we're trying to look at what contributed to the really rapid sea ice loss in 2016, and then the persistence of that ice loss for several seasons. So at the point that this study was done, there was data through June, July, August of 2018. So this was from several years ago. But basically, what was found in this study, and is consistent with other work looking at the 2016 large sea ice loss that occurred in the Antarctic, was that there was a role for tropical teleconnections to influence local winds around the Antarctic and drive sea ice loss. And so this particular study called out the interdecadal Pacific oscillation, its influence on atmospheric circulation anomalies around the Antarctic. You can see those circulation anomalies here, the wind vectors associated with them and the high and low pressure systems, and then sea ice loss that occurred associated with that in the red colors. So there is an advective sea ice component to this, and also a transport of heat from atmospheric circulation that was a contributor to that large reduction in sea ice cover. But the question that was posed further is what allowed those anomalies to be sustained for multiple seasons, and now to the point where we've seen those anomalies sustained for multiple years. And it looked like there was an ocean factor associated with this. So this shows ocean heat anomalies, temperature anomalies, as a function of depths over the top 600 meters of the water column and year, showing that there was this warming, subsurface warming occurring in circumpolar deep water around the Antarctic, that in 2016 or so, those waters were upwelled to the surface. And so they helped to sustain those sea ice anomalies for multiple seasons. And I think there's been a lot of work since then, because the Antarctic sea ice has remained very low, that is suggestive that the ocean is playing a very strong role in changes that are currently underway in the Antarctic sea ice. And so it's led some, like Will Hobbs in this paper in 2024, to suggest that perhaps we've seen a regime change in sea ice around Antarctica, and that is in part associated with the relative influence of atmosphere versus ocean forcing on the sea ice changing over that time period. So in addition to just the sea ice being very low in recent years in the Antarctic, we've also seen a change in the standard deviation, so the variance of anomalies in sea ice. So they've become more variable over time. And there's also this suggestion that anomalies have become more persistent. And so this just shows the autocorrelation of anomalies. These are from 120-month running trend analysis, showing that the autocorrelation, these sea ice anomalies are becoming more persistent as well. And there's a lot of other suggestive evidence that the ocean is playing a very strong role in anomalies in sea ice in the Antarctic in recent years, including the fact that some of our reconstructions of sea ice, which are based on relationships to atmospheric variability, seem to be breaking down in recent years. So there's a lot more to understand about what's happening in the Antarctic sea ice, the role of the ocean, and things like whether this is internally driven, anthropogenic forcing, et cetera. So some takeaways that I want to leave you with. In terms of Arctic change, we've had a lot of discussion about Arctic amplification, and I think there's a lot of reasons for that, in that it's really a defining feature of the warming climate. It results from the strength and sign of multiple feedbacks. That feedback strength, or the factors that drive feedback strength, can evolve in transient climate conditions, and that can have implications for the warming in these regions. And I focus on sea ice, so I want to emphasize that the details of sea ice really matter for these things. The seasonality of sea ice loss, but also, as Patrick mentioned, the albedo of sea ice itself, how much snow you have on top of the sea ice, ponding on sea ice. Those factors matter for things like the strength of the surface albedo feedback. In the Antarctic, it's a really different place. The sea ice processes differ. There's strong teleconnections from the tropics. There's limited to no amplification due to weaker albedo and lapse rate feedbacks, and also a strong role for the ocean. And the ocean also likely is a key factor in recent sea ice losses. And so some questions that I have that I think I'd love to chat with people about through the week is, in terms of Arctic change, we have these defining characteristics, amplified warming in the Arctic, things like that. But models differ a lot in terms of the magnitude and some of the characteristics of that amplified signal. So how can we better use a cross-model analysis of feedbacks, their spatial signature, their transient response, observational constraints, to really narrow that projected uncertainty in Arctic change? In terms of the Antarctic, how do we better quantify and understand the role of the ocean in surface changes in the Antarctic? And there are experts in the room on this, so that's great. The influence of internally driven versus externally forced changes, and why our climate models really struggle to simulate some of the recent observed changes that we've seen in the Antarctic. And they have some real challenges there, and so we definitely need improvements in the models to better understand what's happening in the Antarctic. And then how do similarities and differences between the poles kind of just inform our general insights on climate change and changes in the polar regions? So with that, yeah.
Thanks a lot, Marika. Great comparison to have these two different poles. We have time for questions for Marika. So yes, if you want to use the mic over there so everybody can hear you, and also online.
So in your large ensemble model comparison, the differences in models Arctic amplification depending on sea ice loss and sea ice albedo feedback? And do you think the differences in the models, ensemble models, is more related with the models' ice sensitivity to forcing, or like control climate in sea ice? So, for example, if there is no sea ice in this area, then there is no room for changes in sea ice. What do you think?
I think they're both playing a role, and I think they're also related to each other, in that things like the thickness of the sea ice, the snow cover on top of the sea ice, things like that, which differ quite dramatically across the models, also influence how easily you can melt out regions of sea ice. So if you have an ice thickness bias, that affects how rapidly that ice can be lost in a model. But even those spatial patterns that I showed in terms of the albedo feedback strength, in some of the models you can see quite clearly that they have a strong change in their surface albedo feedback in regions where there shouldn't be sea ice in the summer. And so that's because those models have a bias in their ice extent in summer months. So it's kind of both things are playing a role. And I think, honestly, what this suggests to me is that we should be looking more carefully at these things in our models and across model comparisons to get a better sense of what is actually realistic. If there's some change in the model that's largely associated with a model bias, then maybe those are things we can discount. So, there have been a lot of work trying to constrain our models, using things like the observed record of ice area change or things like that. I think we need to take that one step further and look more deeply, not just at ice extent, but these other factors, like the albedo of the ice itself, the thickness of the ice, albedo of snow, the snow cover over land, those kinds of questions.
Thank you. Yes, maybe King Shua and then Patrick.
Very interesting talk. I have a question for in your first slide, you showed like the 100 years of data, like temperature data. So there's an early warming in the Arctic, like 1920 to 1940s. The magnitude is quite comparable to the recent. So what do you think about the cause of that early warming in the Arctic region? Do you think that is the real signal, or it's kind of the data problem?
I mean, there has been work done looking at that. Trying to go back to that plot. At that earlier warming, and there are probably others in the room that have more expertise on that. I think there are some indications that it is a real signal, and I'm going to forget the details about the previous work done on that. You're talking about the warming here, yeah. So there has been work looking at that, 20th, kind of mid-20th century warming and the factors associated with it. And I've read some of those papers, but it's probably been more than a decade. Does anyone? Yeah, tell.
Maybe there was a lot of aerosols in the northern hemisphere. Mark England had a paper on how that basically suppressed the warming in the 60s to 90s. So it's more that there was a dip rather than, I think that was the
What's the AA rate over that period? Have you calculated that?
I haven't. So, yeah, I mean, aerosol influences are really strong here, which is why, most work suggests that Arctic amplification doesn't emerge until the end of the 21st century. I will say, though, that the actual magnitude of that aerosol forcing is very uncertain. And so we've done simulations with CMIP5 forcing versus CMIP6 forcing. They have differences in their aerosol emissions in the historical record. They lead to really different responses in the climate. So even the magnitude of that aerosol forcing is uncertain.
So I have two questions, if I may. First one, maybe a little shorter, but could be a long answer. So I'm curious, going back to the spatial patterns in the sea ice, albedo feedback, et cetera, I'm curious, could you comment on the differences, the potential differences in like the drift of the sea ice circulation across these different models? Because I've been, playing around with my head about, how models move sea ice around is going to play a really important role in the spatial pattern and also the overall extent changes, I think.
So I haven't looked at that. I think that would be a useful thing to do, is to look at the circulation. And definitely the circulation of sea ice drives the mean sea ice thickness, spatial patterns. And I think you can see an imprint of those spatial patterns in this map, right? That you lose ice where it's thinnest, you keep ice where it's thickest. That affects how effective you can have an albedo feedback. But you also see that differs across the different models. And so I think even just in thinking about how the sea ice circulation sets up the mean thicknesses and how that influences these response patterns is useful. So there's a lot more that I think you could do there in terms of thinking of ice motion and how that can change these patterns and how that differs among the different models.
Yeah, and then going back to Francois' comment this morning about the polar implication, causality of polar implication opportunity, that's another thing that we're hoping to look at with the daily output from the models to see how the sea ice drift. Because I think, even though I haven't done any specific calculations on this yet, I think the changes in drift that we're seeing actually may correspond to some of the slowing of the extent change that we're seeing. Less sea ice moving a little faster could be contributing to the trend that Michael was showing at the slowing of the sea ice. But that maybe is a conversation for a different day. So my second question is going back to the two Manabe papers that you showed. And I looked at my presentation here because I was curious. So in Manabe, the style for 1980, you have that one. That shows so there's stronger amplification in the Arctic than the Antarctic, but it's still there, right? You see amplification. Yeah. However, when you show 1992 paper, that the amplification kind of goes away in the Antarctic, and I wasn't sure, I'm not as familiar with the 1992 paper. Could you talk about why the change in the Antarctic there kind of in the amplification signal is the difference between those two?
So these simulations were done with a slab ocean model. Yeah. And so this is an equilibrated response. Okay, so in an equilibrated response, you do see amplified warming in the Antarctic. It's actually considerably weaker than the amplified warming in the Arctic, but there is an amplified warming signal. That amplified warming signal is present in fall and winter months, much like it is in the Arctic. It's just, and so this is an equilibrated response. Okay. The 1992 paper that I showed is the transient response. And so it's this difference in, the fact that ocean heat uptake has a really strong role in the transient response. But, by the equilibrated response, it's much less. So you actually see, like, if there's, I think Kyle Armour has this nice paper showing kind of century timescale changes in the warming, and you see that the Arctic amplification emerges and then kind of stabilizes and even weakens a bit as some of these feedbacks saturate. And then you see that by the 200 to 300 year time period, you start to see that the Southern Ocean starts to warm rapidly. So it's that equilibrated versus transient.
Thank you.
Yeah.
Thank you, Earl.
Marika, really nice talk. So I have a question related to your last slide about why do models struggle to reproduce trends in the Antarctic. So my first question to you is, do any ensemble members of the latest large ensemble runs reproduce any look like the decadal trends we've seen in observations in both the mean trends and also the trends in the persistence of these anomalies? And if they don't show, any guesses as to what's missing from runs?
So I've mostly looked at this in the CESM large ensemble simulations, and that's the model that we develop at NCAR. So the CESM large ensemble simulations that we have, the CESM2 model has a really beautiful annual cycle of Antarctic sea ice. It looks really nice. We never see a single year ice loss events of the magnitude that we saw in 2016 in all our 100 members of that ensemble. So we also struggle to see increases, the increasing kind of decadal scale trends that occurred prior to that 2016 event. So we don't see that across our ensemble members. Okay, so that model, I think, has a lot of really good things about it, but we don't see the kinds of trends that we've observed in the Antarctic. We do see some things that look quite realistic in that model, though, so I think there's value in probing more deeply. And we've been doing some analysis looking at kind of decadal scale changes in persistence and variance of sea ice. And we do find decadal periods, even in our control simulations, that have some similarities to the changes in variance and persistence that we're seeing in the last decade in the Antarctic. So we're trying to understand, using the model, why we have these changes in variance and persistence of sea ice. And it actually looks like it's associated with circumpolar deep water, shoaling, and being more kind of accessible to the sea ice. So I think there's value in looking at these models and trying to understand, what they do simulate. I think that the reason that, in general, the models struggle to simulate changes in Antarctic sea ice like we've observed is, well, atmospheric scientists would probably tell you it's clouds. Oceanographers would tell you it's the ocean. I work on the sea ice component in the model, and it's perfect. No, but I think that how we simulate the ocean is a challenge, and we're doing it at these coarse resolutions. We're not resolving eddies. We know they're important there. We actually have some simulations with a 10th, so our standard model is a 1 degree ocean model. We have some simulations with a 10th degree ocean model. They actually seem to have, we have like, I think 8 ensemble members. One of those ensemble members seems to look a lot more like what we've observed. So I do think we need to likely go to higher resolution in our models, or improve things like our eddy parameterizations in these models, and better simulate the Southern Ocean. But again, a cloud person would tell you it's the clouds, so
Thank you.
Okay, is there one burning question? Okay, maybe, yeah.
Sorry to keep you all from lunch. Marika, great talk. Ethan Campbell from UW. My question is actually about that perfect sea ice component. So I know we have a sense that the boundary conditions matter a lot, and that if you force Antarctic, if you force a model with observed winds, you get a better state, and if you initialize it with more accurate sea ice thickness, you get a better state. But I'm curious, within the sea ice component, what would you identify as key areas, key challenges, key areas where there might be deficiencies that could be improved for Antarctic sea ice specifically?
About Arctic sea ice specifically?
Sorry, for Antarctic specifically.
For Antarctic. Well, I mean, one of the things that, and there's been a lot of movement on this and development on this recently, are things like wave ice interactions. So we don't simulate that in the generations of models that I was showing here. We're actually trying to get that into our CESM3 model. It's one of the things that's been taking some time. But I do think in the Antarctic, we know that there are big waves, there's big swell that influences the flow size distribution of sea ice. How many small flows you have affects how much lateral melting can decrease your sea ice cover. And so there's a strong albedo feedback associated with that. And so I think it's likely to affect, both the transient changes, kind of large-scale changes, but also how an individual storm affects the sea ice in the Antarctic. So I think that's important. I've done much more work on factors that drive changes in the surface albedo, and I think that there's definitely room for improvement there as well. How we simulate snow on top of sea ice in particular, we don't include often things like blowing snow. We know that's actually really important in the Antarctic as well. How that redistributes snow on the surface, these kind of processes that have very high spatial heterogeneity that affect how much heat you can get conducted through the sea ice, which affects the sea ice mass budgets. So there's definitely, I joke about the sea ice model being perfect. It's not, and there's lots of work going on. But I think for the Antarctic, wave ice interactions is definitely a key thing.
Thank you. I think we're going to leave it at that for this morning. Lunch is going to be same place as coffee on the courtyard outside, and we'll reconvene at 2 p.m. And you've heard Claudia, she's ringing the bell. When it's time to come back, so that's the signal. Thank you all. Thanks, Marika, again, and thanks to all our speakers this morning.